Welcome back to this lecture on algorithms. In its second segment, we're going to discuss pseudocode, and we're going to give our first example of an algorithm. So pseudocode is a language. In particular, it's the language used to define algorithms. A pseudocode is somewhere between a natural language and a programming language. Now remember that a natural language is very expressive, but it's also very ambiguous, whereas a programming language is much less expressive and much more strict in its syntax, but it's also unambiguous, which is why we use them to program computers. So, what are the features of a good pseudocode language? Well, first of all, like a programming language, it must be unambiguous. A pseudocode must specify a very definite algorithm, so there can't be any ambiguity in the language or the pseudocode. So in other words, pseudocode is like a programming language in that it's unambiguous. But it must also be more abstract or somewhat less strict than a programming language in terms of syntax. This is just to make it less tedious to write the pseudocode. So maybe you don't have to worry too much about semicolons or curly braces and all these kind of small details that are not very important in the definition of the algorithm. They are just syntactical features. So in conclusion, the pseudocode is better than a natural language because it's unambiguous, but it's better than a programming language because it's more abstract and not as strict. It's a little bit easier to write pseudocode than in a programming language. However, it must be said that pseudocode is typically closer to a programming language, so it's still pretty strict, at least the one we're going to use in this class. So to illustrate the pseudocode we're going to use in this class, let's go back to our example problem that said, find the location of a target object in a finite sequence of objects. That's the general problem that we came up with in the first segment. Now notice there's one slight difference between the statement of the problem here and the earlier one. We inserted the word finite. We want to make sure that the input to the algorithm is finite. Otherwise, it's going to be hard to guarantee that the algorithm terminates on every single instance in a finite amount of time. Now, let's discuss one possible solution or algorithm for this problem. We must always start our algorithm specification with a comment that clearly states the behavior of the algorithm. In particular, it defines its inputs and its output. So this algorithm will take as input first a target object and second a sequence or finite sequence of objects. Then this algorithm will return an integer which will be the index of the target object in the sequence if it was found. Remember that every element in a sequence has an index or a position from 0 up, so that will be the output of the algorithm. And in case the object is not in the sequence, the output will be -1, which is not a valid index. So it will be easy to distinguish whether the object was found in the sequence or not. Since our algorithm takes inputs and returns an output, it's a function, as we define them mathematically, except a function with more than one argument. So our algorithm or our pseudocode description of the algorithm will start with the keyword function, which is required. Then we're going to give a name to this algorithm or function. Since our solution will be to scan the items in a sequence sequentially from 0 up or linearly, we're going to call this algorithm linear search. The name of the algorithm is also required. Please make it short but meaningful. The third required element on the first line of the algorithm is the list of inputs to the algorithm. In this case, there must be one input, which is the target, which is preceded by a colon and then the type of element we're talking about. In this case, it's a very generic type called object. Then there's a comma separating successive inputs, and the second input is a set of elements a sub 0, a sub 1, dot, 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 a sub n minus 1. Notice there are n elements in that sequence from 0 to n minus 1, and those elements are preceded again by a colon, and by a type, in this case, a sequence of distinct objects. It's just a convenience that we require the objects in the sequence to be distinct. There are no duplicates. So notice the arguments must be surrounded by, or the inputs must be surrounded by parentheses. They must be separated by a comma, and they must have a name, and they must be typed. So there must be a preceding colon and a type. And finally, the last required element on the first line of the algorithm must be, because we're defining a function, there must be a return value, and we must specify the type of that return value. And the way we do it is by adding a colon outside or after the inputs, and then the type of the return value, in this case an integer. Now realize that together the comment and the first line of the algorithm fulfill the first two requirements of an algorithm, namely that both its inputs and outputs be completely specified. Now we're ready to specify the heart, the body of the algorithm, the sequence of instructions that it will execute. So the first line will be an assignment statement that assigns the value 0 to the variable I. Notice we're doing pseudocode, so we are very close to a programming language, but we don't need to bother with semicolons and other details. In particular, we don't need to declare the variable I. It will be inferred from the pseudocode that it's a variable of type integer because we're assigning an integer to it. So we assign 0 to a new variable I. This is the symbol we're going to use for the assignment statement. It's a colon and an equal sign. I'm specifying here, as I'm going through this example, all the requirements of all your pseudocode algorithms in this class, by the way. So make sure you take note of that. Now that we have initialized the variable I, we can start a loop. And the loop is going to go through all the values of I from 0 up. We will stop when we've reached the end of the sequence or when we have found the target. And when have we found the target? When a sub I, which is our index variable, is equal to the targets. So while that's not the case, and we haven't reached the end of the sequence yet, we just look at the next element. In other words, we increment the variable I by 1. And that is this line is the only instruction in the body of the while loop. So when do we exit the loop? Well, when this condition is false. And there are two possibilities for this condition to be false. Either it's because I is not less than n, in other words, I is equal to n, which means we have reached the end of the sequence without finding the element, or we have found a target and this condition is false. That's the only two possibilities for getting out of the while loop. So how do we determine after the loop how we got out of it? Well, we're going to compare the value of I with the value of n. So if I is less than n, the only way we got out of the loop is because this condition was false. In other words, we did find a target and we found it at position I, so we can return the value I. In the other case, when this condition is false, that means I is equal to n, we did not find the target in the sequence, and therefore we must return the constant -1. And this is the whole body of the algorithm. Now, even though you already studied this algorithm in your Introduction to Programming class, please realize that it is extremely difficult to design your own algorithms and come up with a correct solution. So make sure you understand why this algorithm works. And as an illustration, let's go through one trace of this algorithm. Again, that's not a proof that it is correct, just an illustration. Let's say the arguments or inputs to the algorithm are the following sequence, 2, 5, 1, 12, and with the following mapping to the names of the inputs. And the target is the integer 1. So the trace of the algorithm starts with the first line, obviously, where I is assigned a value 0. So now I is equal to 0 after the assignment. Notice we don't have an assignment here, just an equality. That's a Boolean condition for the value of I. Then we go to the second line and we evaluate the condition of the while loop. And this condition is true since I is less than n, and a sub I, which is a sub 0 or 2, is not equal to the target 1. So we increment the value of I on the third line, and we go back to the condition in the while loop. This condition is still true for the same reasons, namely I is less than n, and a sub 1, which is equal to 5, is different from the target 1. So we go through the body of the while loop again, we increment the value of I is equal to 2. Now this time the condition is false. Why is that? Because I is still less than n, but a sub I, which is 2, is equal to 1, and that is equal to the target value of 1. Therefore, the condition is false. We get out of the loop. Now, we check the next line on the algorithm that says, is I less than n? Now, the answer is what? Well, 2 is less than, what is the value of n in this case? That's right. The value of n is 4, because there are 4 elements in the sequence. Remember, the index goes from 0 to n minus 1, but n is equal to 4. 2 is less than 4. Therefore, we haven't reached the end of the sequence when we exited the loop. Therefore, we found the target. The index of the target is the value of I, which in this case is 2, and that is the return value of this algorithm.